I have actually been with CERT for about 15 years, and I've worked on a bunch of projects of which these are 4, and that all kind of tie into each other. So what you're going to get is something of a autobiography, a professional autobiography between these 4 things, but they all build on each other in interesting ways, which is why I'm talking about them today. So the first is the SCI CERT Coding Standards. We have 5 coding standards right now, one for C, C++, Java, and Perl, and there's also a space for Android-specific rules. So the CERT C and C++ ones have been published in, both in book form and in ebook form. The ebooks are freely downloadable from these websites. They were published in 2016 and 2017, respectively, for C and C++. And we also have a Dead Tree edition of the Java coding standard. And all these coding standards are available at the following web link, which kind of has our current latest and greatest. We have been updating them as the languages evolve. C is evolving very slowly. C++ is a bit faster, and Java is, Java's having lots of updated version numbers. I think they're on Java 19 right now, but they release new editions every 6 months, and that's a lot. Well, I'm not sure just how much that relates to how many changes there are in the language. They're mostly bug fix versions. I'm actually going to go ahead to this slide, going into the details of the CERT coding standards. I'm primarily focused on C, but this applies to all the CERT coding standards. They are all divided into rules and recommendations. A rule, a secure coding rule, is something that if you violate it, you have insecure code. You could get pwned. In particular, it has to satisfy these 3 conditions. Violation is likely to result in a defect, and the defect may be an exploitable vulnerability. The code does not rely on the intent of the programmer. A third party can take a look at your code and say yay or nay whether it complies with the rule. This requires a degree of specificity of the rule. The rule can't just simply say, buffer overflow. Well, what is and isn't a buffer overflow? This actually just happened last week. One of my coworkers said to me that ChatGPT was hallucinating again because it claimed that some code had suffered from a buffer overflow. And I looked at the code, and the code simply said int buffer equals int max, buffer equals buffer plus 1. I guess you can argue that that's a buffer overflow, but it certainly isn't what I normally think of as buffer overflows. I simply said to him, if there is a fault here, it does not lie with ChatGPT. So, getting back to here, the point is that two people that look at the rule and look at some code can say yay or nay whether the code agrees with the rule or not. If they don't agree, then either they don't understand the code, or they don't understand the rule, or the rule is ambiguous. And I know this because I spent a lot of time arguing with other coworkers about the rules and trying to hone them up and make the rules precise enough so that we could agree. The recommendations are like the rules, but they're kind of wannabe rules. They come close to matching these, but for one reason or another, they don't quite fit up to being secure coding rules. So what's our ebook are the rules, and the recommendations are kind of again the B material. Okay, so what we're going here that I had skipped past was simply the set of anatomy of a single CERT recommendation. The actual recommendation is not so important. The important thing is the components. Each recommendation and rule consists of a title. The title is going to be concise, and then there'll be an introduction which is precise. That is, the introduction has exactly the details of what code has to do to comply or not comply with the guideline. And the title it's more important for the title to be quick and short rather than exact. So that's our concise versus precise dichotomy. Every rule or every guideline, and when I say guideline, I mean either a rule or recommendation. The guidelines apply to everything. Every guideline has both non-compliant code and compliant solutions. The non-compliant code tries to conform to every guideline we have except for the one in particular. This is code that has exactly one error in it. It's actually it's not only difficult to write code that complies with the guidelines completely, it's even harder to write code that violates exactly one guideline without violating a second one. So it's important to have high quality code examples, even if they are showcasing bad practices, mainly because not only is this code publicly available, but we are saying this is code above is bad code, don't write this, and this code is good code, feel free to cut and paste this into your own software. Every compliant solution is there to show here's one way to modify your bad code to make it good code. So they're all attempts to solve the various problems. What I have here is some boilerplate that comes after the recommendations, after the code examples, such as a bibliography, related guidelines. The most important stuff after this is the risk assessment, because the risk assessment contains several metrics that can show you things about the severity and the remediation costs about each rule, and I want to go into these more precisely because this becomes important in the course of the rest of the lecture. So the three metrics for risk assessment are severity, likelihood, and cost. Severity basically says if your code violates this guideline, what can happen to you? Can someone just simply crash your program? Well, that's not necessarily so bad. My mom can crash a lot of programs. She doesn't know how she does it. She always says to me, "Dave, I didn't do anything." And you still did it, Mom. And if you can crash a program, you generally can't necessarily do the next two things. The second thing is, we're right, data integrity violation, information leak. Get the program to reveal your password or your credit card number or something. That's worse than crashing. And if you can get your program to reveal information, you can usually crash it easily. And that's why information leakage is at a medium severity. The high severity is remote code execution or privilege escalation, that is, defeating a security sandbox, such as what your web browser provides. And that's the worst thing, because if you can do that, you can do the first two items easily. But just doing the first two items doesn't mean you can do remote code execution. The probability is simply how likely is it that you're going to get pwned if your code is non-compliant. And the third item, remediation costs. This is the one I want to focus on today. In particular, how expensive is it to fix your code? Well, it's two questions. How expensive is it to detect that your code violates the rule? And if it does, how expensive is it to fix it? Can this be done automatically or manually? There's lots of static analysis tools that will claim that they can detect violations of your code, but do they work? Do they suffer from false positives? Do they report a lot of errors that are there or that are not there? Do they miss a lot of errors that are there? In fact, if you look at our coding standards, you'll see that every guideline has a long list of static analysis tools that claim to detect violations of the rule. Unfortunately, we cannot vouch that those are correct. We've generally trusted that the people who say, our tool detects violations, we generally trust that they are telling the truth. And for the repair, we were assuming the theoretical existence of an automated repair tool. There weren't, when this came out 20 years ago, there really weren't automated repair tools, at least not for C. So we were kind of theorizing, but today there are. And the landscape is a little different than we envisioned. So I want to talk about that coming up in a bit. Finally, each of these metrics winds up with a number between 1 and 3, and you can multiply those numbers together to produce a product, which is a number between 1 and 27. And we just simply categorize the rules into 3 buckets, where the inner bucket of priorities 12 through 27 are the most severe the ones that are most likely to get you to have attackers run remote code, the ones that are most likely to get attacked, and the ones that are the easiest to fix. And then the lowest priority rules are the ones with priorities 1 through 4. These are the ones that can cause the least harm, that are the hardest to attack, and that are the most expensive to fix. So the argument is this is kind of a way of ordering the guidelines from in a priority of deal with these ones first and those ones last. If you don't like our ordering, feel free to use your own. This is one that we pretty much arbitrarily chose. Okay, so that was the first project. Second project is, SCALE, which stands for the Source Code Analysis Lab. And this follows pretty easily from the coding standards. Once we have a set of coding standards, we can simply say, well, here's a code base. Does this code base comply with the coding standards? How badly does it violate it? How many violations are there in this code? And as you can see, this becomes a simple business proposition. Give us your code, and we'll tell you how many problems there are with it. We'll run a bunch of static analysis tools and report we could just report all the findings, but that's pretty simple. Anybody can do that. We will also audit them and give you some alerts that we know are true positives, and we can also say, this other set of alerts, these are false positives. We just want you to know that we did this work, but you can ignore them. We also started off with a certification program where if you fix all the problems that we find in the code, then we could give you a certificate and list your code in a registry of scale compliant code. Unfortunately, we never found code that quite made that mark. That was not meant to be funny.
It's sadly fun.
It's funny, not funny, ha.
Yes.
All right. Well, so this was the scale process that we had. We basically had a couple of machines with a menagerie of static analysis tools. You run all the tools in your code, and you get a set of diagnostic alerts. You unify them to one big happy set, and then some poor slob of an auditor would go through and identify the true positives and the false positives. Again, the false positives, initially we would just remove the false positives, and later on we decided, we'll just tell the clients that we produced these false positives just simply to show that we did work. Now, there were often lots more alerts than we could look at, and so we wound up giving them a list of probable violations. That is, here's a small list of true positives, here's a smaller list of false positives, and here's a huge set of alerts that we got where we just didn't have time to audit them all. And this is what we would give to people. And I was often the last person. When we would give code assessments of everything, I was often the last person because I would often have the worst news. So in fact, the news was bad. As we said, the number of alerts that we got was funny, So what I have here is some statistics from the very first couple of code bases that we audited in the mid-2010s, where out of 5 C and C++ code bases, we had these stats, which basically amount to about 1 alert per every 3 lines of code. And the average lines of code that we had in the code bases were about 2 million. And doing some back-of-the-envelope calculations, where we took this statistic of 117 seconds to audit an alert, that's 2 minutes, looking at a single alert and saying yay or nay. I computed that it would take 15.5 person years to audit all the alerts that we would get from the average code base. How many people spend 15.5 person years looking at code, at a single code base without changing it? Is there any code base that actually has not been changed since 2010 that people are actually using? Furthermore, I extrapolate that if it takes 117 seconds to repair a single alert and only 32% of the alerts are true, then it would take 5 person years to fix them. And the 117 seconds and the 32% come from this study called the Google Find Bugs Fix It, done by Bill Pugh with Google on some Java code. Yes, it's Java, not C, so I'm kind of extrapolating that this applies universally. But the main point is that the set of alerts that we get from tools is a true deluge. There's no way I can audit them all. our team can't audit them all, and I don't really, well, there's just too many to deal with. That's the fundamental thing. So let me skip this slide and move ahead to the next subject, which is our attempt to redeem this software. The software that has so many thousands of alerts, and I've seen like 150,000 alerts in software. I don't know if all of those are true. I only was able to audit about 2,500 of them. That was the last one I did. So the idea is, this is a research project that, and I think I spoke about this last year. You might think it was initially an attempt to fix code, but ultimately the real thing was to try and cut into the deluge of alerts. So our automated repair tool was designed mainly to fix code, but only make cheap local fixes like what we do here. If we're concerned about A plus B overflowing, we basically just insert this safety code that checks for overflow and has some error handling in it. And the idea being that I've seen repair tools that will say change the code by changing everything in the code. To say stop buffer overflows, convert every pointer into a fat pointer. You can certainly do that. It slows down the code. It makes the code a lot harder to read by putting these macros inside, all over the code. Definitely a fix that is very disruptive if you're still developing with the code. So what we wanted was a tool that would make cheap local fixes, so that you could just simply say, I like this fix, I don't like that one. And you could individually pick fixes, but hopefully you wouldn't need to do that. You could just simply fix 100 alerts and just trust that all of the fixes were good and would not break the code. So that was important, not to break the code. All right. We specifically focused on a small list with the notion of certain rules to repair, with the notion that we could add more rules later on. So we focused on these rules, null planar references, which you can fix by just inserting a null check, uninitialized variables, which you can do by setting them to 0, or ineffective code, that is code that basically does nothing. Something like a go-to label that's unused, or an if block that's always true or always false, in which case, you can just remove the code. A theory is, if you're using this without CI, then first of all, you can first read this without the red blocks, in which case you're using a static analysis tool. The tool gives you reports and it gives you alerts, and you have to decide whether each one is true or false. And as I've explained, that can take a ridiculously long time. If you add a repair tool, then the repair tool would simply get the output of the static analysis tool. It would say, I can repair this subset of alerts. Here's a set of repairs, and those repairs go into your IDE, and then you can just decide which of them you like. Ideally, you would just simply say, I like them all, make it so. Of course, in this group, we love CI, continuous integration, and we would hope that you have a DevSecOps pipeline involved, in which case your DevSecOps pipeline includes, among other things, a version control system like Git or Subversion, and your static analysis tool. And this stuff all runs in the cloud somewhere, and gives you the set of alerts. If you don't use a repair mechanism, then you get a set of alerts from the cloud every time you commit code. If you integrate our redemption tool into your CI system, then it runs when the static analysis alerts, produces repairs, and the repairs go into a pull request. It goes into your version control system, and then all you have to do is look at the pull request and say, do I approve of this pull request, or do I want to adjust it at all? And we already have interfaces for accepting or rejecting pull requests. So you may have seen this before. This is our favorite DevSecOps pipeline, and in particular, the redemption tool applies primarily to the development and testing. Ideally, developers will run the repair tool and the static analysis after they do any development. Testers will run it as well, mainly to capture anything the developers happen to miss, and it might be run as part of the delivery process as well. So our goal is that we want the redemption tool to be trustworthy, that all its repairs are good, and that they don't break code. And the way we accomplish this is by focusing on what each CERT rule does. Most of the CERT rules forbid what in the standard is known as undefined behavior. Undefined behavior is basically where the ISO C standard says if you do this kind of thing, like you have reference a null pointer, the behavior is undefined, and that means the standard imposes no constraints on what happens. The platform is free to play the game of life. It's free to stop the program. It's free to summon the nasal demons. Anything can happen. Or rather, whatever happens, it's not the compiler's fault. It's your fault. So, yeah, if you have undefined behavior, may God have mercy in your soul, for your computer will not have any. So, the argument is that our redemption tool takes undefined behavior, or at least certain kinds of undefined behavior, and converts it into an error condition. Instead of dereferencing this null pointer, it simply says, is this pointer null? If so, then run this error handling code, which might make your program crash, but it's better than having your program do undefined behavior. We did 3 rules, or rather 2 rules and 1 recommendation. When we discovered that the rules, we were hoping the rules could repair 80% of code correctly. In fact, they repaired 100% of code correctly when we ran them. The recommendation also correctly ran all the repairs, repaired all the code, but we decided that we didn't like its repairs. Its repairs removed code that was ineffective or unused. It could be removed without changing the behavior. So we didn't change the behavior of the code, but often what we took out were things that should probably have been left in. For example, this rule, MSC 12, basically says remove code that has no effect. So one example of code that has no effect is a goto label if there's no goto statements that send you that label. If anyone here has ever used the Flex or the Bison parser generator in C, or Yak, that's what I was thinking, not Flex, Yak. They basically create a state diagram or state table in C, and the states are represented by goto labels. So, if you want to go to state A, then you say go to A. And as you might guess, there are often labels there that nothing else ever goes to. So it creates a lot of, Yak and Bison create a lot of MSC 12 violations. And while we can remove those labels that are unused, it's probably a bad idea from a maintenance standpoint. So therefore, we disabled this repair, and we enabled only if you set an environment variable when you run the code. Okay. What I have here is I'm gonna skip the video, but what you're seeing here is effectively a demo photo of Visual Studio Code that has some repaired code. The unrepaired code is in red, and the repaired code is in green. So you see we've added some initialization values down here, and up there's some null checks in macros. I don't have time for this video, but in particular, what it shows is that you can remove any one of these things that you don't like if you want to. That's part of VS Code's way of handling merge requests. We hope to get this tool out to more partners in the DoD in particular and the government in general. We also hope to add more CERT rule support. If we support 10 rules, we figure that will capture about 50% of alerts in at least the daily sample we looked at. If we cover 17 rules, then we would cover 60%. We could also support more static analysis tools and more IDEs. Right now we support Visual Studio Code. So it has a potential for a lot of growth, and it is currently available as an open source code base on GitHub. So the final thing I want to talk about is simply how building this repair tool has changed the way we think about the CERT standards. So in particular, remember that I talked about the remediation cost, and it simply asks 2 questions. Is a violation of this rule detectable by static analysis, and is it repairable? And as I said, as I noted before, if a rule is repairable, but it's not detectable, then we use the high value there. And we don't distinguish rules that are repairable but not detectable from rules that are not repairable and not detectable. And what we discovered is that in redemption, there are several rules that are repairable but not detectable. Null pointers is a perfect example. You can detect null pointers but not reliably. Every tool that I've seen that claims to detect null pointers either has false positives, they report null pointers when there aren't any, or the false negatives. They fail to detect null pointers that actually can be dereferenced. And furthermore, as I said, every rule has a bunch of static analysis tools that claim that they detect violations of the rule, even if the rule claims that it's not detectable. I mean, what's going on there? Are they lying? Well, the answer is they're not lying. They are just simply relying on the fact that our definition of detectable was kind of fuzzy and nebulous. So what we've done is we've updated our definitions for detectable and repairable. Now, the definition of detectable says, can a static analysis tool determine if code violates the guideline with high accuracy and precision? In other words, is there an algorithm that will determine, if the code violates the guideline that has no false positives and no false negatives? And I shouldn't say no, but almost no false positives and almost no false negatives. So that way we can say this rule is not detectable, even though there are tools that claim to detect it, because that just simply means that, yes, the tools will detect some of the cases, but they may fail, they may have false positives or false negatives or both. Likewise, repairable is now defined differently. Can we automate a repair tool, fix an alert by making local changes, and can the repair be guaranteed not to break the code, even if the alert is a false positive? So if you tell me null pointer alert on line 10, I can repair the code even if there's no real null pointer alert. All I do is I add a null pointer check, and if there's no null pointer alert, the check is superfluous. It's basically a no-op. It doesn't do anything. And this also makes the definitions for detectable and repairable independent. So a rule can be repairable but not detectable, or vice versa. Okay, so quiz time. Here are 3 CERT rules. The first CERT rule about null pointers is repairable but not detectable. And these next 2, I've left blanks there for you to help fill in. So, free dynamically allocated memory when no longer needed. This is the rule against memory leaks. If a alert says memory is leaked on line 10, the memory owned by pointer P is never freed. Yes, you can in theory add a free. Does that fix the code? So, show of hands, how many people think that this rule, which is Mem 31, how many think it's repairable? How many think it's not repairable? How many are asleep? All right. So ultimately what I'm saying is that this is not a repairable rule, because sure we could add that free pointer in, but what if it's a false positive? What if the pointer has already been freed and we add a second free pointer? Well, that's a double free, and that is a major vulnerability, very easy to exploit, and therefore this rule is not repairable. Okay, so second question, I'll quickly go through this. Exclude user input from format strings. Format strings should usually, these are functions like printf that they typically have string literals. And while you can pass in something that's not a string literal, it's done so rarely that I would simply say, if you're passing something that's not a string literal, then I would just go ahead and flag that as a true positive of this rule. So anyone care to suggest that whether this is detectable or not? All right, well, it is detectable by that argument. And so this is, what we've done is we've been spending the last couple of months going through all the rules in CERT, C, C++, and Java. We still have to do Perl and Android, and just simply update the remediation costs. Instead of simply making them individual numbers, 1, 2, or 3, we're just simply saying, yay or nay, it's detectable, and yay or nay, it's repairable. So this is an improvement which should hopefully make the CERT standards more up-to-date, tuned in with the decade, and able to handle automated code repair tools like redemption. but not just redemption. This also simplifies the auditing process because you no longer have to audit every single alert from every single rule that comes in. If you give me an alert of a null pointer, those are really hard to audit, but I can simply say, I'm not going to bother auditing this. It's just easy to repair this automatically. You can easily repair it without breaking the code, so don't audit it. Just go down to the repair alert item here. If you give me an alert that is not repairable but is detectable, then that means that the tool that claimed the alert should be following an algorithm that has no false positives or no false negatives, so I shouldn't need to second guess it. So for a detectable alert, just send that to the developers saying, don't waste my time with this rule. Just go ahead and fix it. So it's only for the alerts that are neither repairable nor detectable that require an auditor's time to look at it. In other words, by applying this change to the remediation cost definition, we basically reduced the set of rules we have by, well, officially by 3 out of 4, 75%. And that should hopefully make the audit process a lot simpler and speedier. Okay, and that is the presentation. Again, the CERT rules are all on securecoding.cert.org. The redemption tool is available on GitHub, and I'm available with this contact information.
Thank you, David.